Capturing clear images in the dark is a classic challenge in computer vision. Traditional methods often struggle with noise or require clean reference images that are difficult to obtain. This paper presents a breakthrough approach, using near-infrared, or NIR, light to guide the reconstruction of noisy RGB images in 3D space. By using a 3D-Aware neural model, the system can effectively see in the dark without ever needing clean, noise-free RGB data for training. The core idea is to leverage the structural consistency of 3D space. By using a volume rendering framework, the model aggregates information from multiple viewpoints. While standard neural networks often struggle with noise, this architecture is specifically designed to treat NIR as a structural guide. By feeding NIR data into the RGB network, the model learns to prioritize the clean structural information from the NIR sensor while filtering out the random noise present in the RGB input. A common problem in neural rendering is the checkerboard effect, where high-frequency noise is misinterpreted as structural detail. The researchers discovered that standard positional encoding, which maps coordinates to higher dimensions, was overfitting to this noise. Their solution is an NIR-modulated positional encoding. Instead of applying encoding to the coordinates directly, they apply it to the NIR features. This acts as a frequency-aligned filter, amplifying the clean structural frequencies while suppressing the random noise. Even with structural guidance, there is a fundamental ambiguity. A single NIR value can correspond to many different RGB colors. This often leads to blending or muddy colors in the final output. To solve this, the authors introduced a Color Code MLP. This component learns a probabilistic distribution for colors, allowing the model to map a single NIR value to multiple plausible RGB outcomes. This effectively resolves the ambiguity and preserves the vibrant, diverse colors of the original scene. The results are striking. Across both synthetic and real-world datasets, the proposed method consistently outperforms existing state-of-the-art techniques. Whether dealing with moderate noise or extreme darkness, the model maintains high structural integrity and color accuracy. Quantitative metrics like PSNR and SSM confirm that this 3D-Aware approach is significantly more robust than traditional 2D fusion methods, proving that 3D consistency is key to high-quality low-light enhancement. While this method is a significant step forward, it does have limitations. Currently, it is designed for static scenes, meaning it cannot yet handle dynamic motion. Additionally, it relies on accurate camera calibration. If the RGB and NIR sensors are not perfectly aligned, obtaining the necessary poses becomes difficult. Future work will likely focus on extending this framework to dynamic environments and improving robustness to sensor misalignment, paving the way for more practical, real-world dark imaging applications.